All right, so let's start looking at the problems in the tutorial one by one. The first problem asks you to find out the adjoint operators for I ddx and d square dx square in L2. So this is the space that we're interested in. And let us start by looking at the operator I ddx. Okay. Now, let's remind ourselves how to calculate the adjoint operator. So first, add the operator on some vector and then take the inner product of this vector with another vector, okay? And if you have any other operator such that this inner product is equal to T dagger F, G, then we say that T dagger is the adjoint of the operator T, okay? Now I use T dagger, but I can as well use another symbol here, B or C or whatever it is. And if this relation is satisfied, we say that C or B or T dagger, whatever it is that I'm using here, is the adjoint of the operator T. If it turns out that the adjoint of the operator T is or the operator T itself, then the operator is called a self-adjoint operator, okay? Now I'll be using the definition of inner product, which is f star of x, g of x, dx. The space is between minus infinity and plus infinity, okay? So let's start by looking at the ddx operator. Let's evaluate this left-hand side, whatever this guy is, okay? So I want to evaluate f I dg dx, okay? So this is equal to minus infinity to infinity f star of x I dg dx dx, okay? Now the way to approach this problem, as we have demonstrated in the class also when we talked about the ddx operator, is to do a integration by parts. So let's do an integration by parts. So this is I. Now I will imagine that this is my dv and this is my u. So the formula is uv minus integral v du. So this is f star of x. The integral dv is just v, which is g of x, between the limits infinity, minus infinity, and plus infinity, minus integral v du. V is g of x, du is df star, which I can write as df star dx dx. Okay. So this is nothing but, now the first term, which is f star g between infinity and plus infinity, goes to 0 because I'll assume that these are all normalizable functions. And for all normalizable functions, they should not keep growing at infinity. They should all die down at infinity. So these are well-behaved functions that vanish at infinity. So this is equal to minus I integral minus infinity to infinity df star dx g of x dx, okay? Now I can write this as integral minus infinity to infinity I df dx star g of x dx, okay? And you recognize this as simply I df dx, or rather tfg, where t is I ddx. Remember that when t is taken to the left on the bra, the I becomes a minus I. So which we find that the operator that satisfies the relation ftg equals t dagger fg is the operator I ddx itself. So the operator I ddx, the Hermitian conjugate of this operator, is the operator I ddx itself, okay? This means it's a self-adjoint operator, okay? So let's do the same thing for the operator. Our next operator is d squared dx squared, and we will do the exact same thing again, but except that in this case we have to do the integration 2 times. So let's again evaluate f dg. This is equal to minus infinity to infinity f star of x d squared g dx squared dx. Okay. So again, just to be very explicit, I can write this as f star of x ddx of dg dx dx. And I will do an integration by parts. This is my dv and this is my u. So this is again equal to uv f star of x. B is integral ddx dg dx dx, which means it is simply integral of d of dg, which is dg dx. This is dg dx in infinity and minus infinity minus integral v du. So v is again dg dx, and du, which is df star, can be written as df star dx dx. Again, I will assume that these are well-behaved functions, and f star and dg dx, everything goes to 0 at plus minus infinity. Now, on what remains, I will do another partial integration. If I do another partial integration, remember that I am taking the two derivatives from g, and I want to transfer these two derivatives onto f star. That is my goal. Okay. So I will do another partial integration here, and I will assume that this is my excuse me, dg dx times dx is my dv. So this is equal to again uv, which is g of x df star dx between infinity and minus infinity minus integral sorry, there is an overall negative sign here, so this becomes a negative and this becomes a positive, plus v du. So this is g of x d square f star dx square dx. Okay, again the boundary term vanishes for reasons that we just described, and I can write this as integral minus infinity to infinity d square f dx square star. Because the operator d square dx square is manifestly a real operator, I can write that thing as d square f dx square star times g of x. And you recognize this as t f g, where t is your second derivative operator. So in the space L2 minus infinity and infinity, we again find that d square dx square dagger is also d square dx square, which means this is also a self-adjoint operator in this space. Remember that this might not be true if we are considering a different space and if the boundary terms don't vanish neatly as they did in this case. Okay? So that is the solution to the first problem in the tutorial. Okay. So moving on, what's the second problem? What is the representation of the X operator in the P basis? Now, I will do this problem at the end. Let us do the other ones, and then I'll come back to the second problem, because there is other things that I can develop that might help understand the second problem better. Okay. So instead of the second problem, I will talk about the third problem. The third problem states that I need to find the Fourier transform of a Gaussian function. And this is a routine calculation, but one that is very important because you would be dealing with Gaussian functions when I talk about wave packets starting tomorrow. So let us work out the Fourier transform of the function f of x, which is 1 over square root of pi a square exponential minus x minus x prime the whole square divided by a square for some constant x prime and a. Okay, all right. Now remember that the Fourier transform of this function, of any function, is simply given by f of p would be 1 over square root of 2 pi h bar integral minus infinity to infinity e to the ipx f of x, and then I have to integrate over dx. This is the definition of the Fourier transform. So let's plug this function and then evaluate the Fourier transform. So f of p for this function would be 1 over 2 pi h bar. Sorry, there has to be a px over h bar here. So just for consistency, yeah. Um, so I'm going to do something that I probably shouldn't do, but I will do it nevertheless. I will set h bar equal to 1, so I don't have to carry multiple factors of h bar. Okay. We can put the h bars in later, or you can figure out how to put the h bars in later if you want. So I'll set h bar equal to 1 for this problem. So f of p would be 1 over square root of 2 pi. There is a 1 over square root of pi a square minus infinity to infinity e to the ipx exponential minus x prime the whole square over a square dx. Okay. Now I'll do a slight change of variables. I'll call y equals x minus x prime. And notice that the limits don't change and dx is also the same as dy. So I can write my f of p as 1 over square root of 2 pi, 1 over pi a square. So this becomes minus infinity to infinity e to the ip. X is now y plus x prime e to the minus y square over a square dy, because dx is same as dy. So I can pull out the e to the ip x prime because that has nothing to do with the integration over y, because it's just a constant. So this is square root of 2 pi, square root of pi a square, minus infinity to infinity, e to the ipy minus y square over a square dy. Okay, now I have to integrate this guy. Now to integrate this guy, notice that I can write this quantity minus y square over a square plus ipy that appears in the integrand as a complete square. I just have to complete the square. So with a little bit of algebra, you can actually work out that this quantity can be written as minus 1 over a square y minus ipa over 2 quantity square, excuse me, minus p square a square over 4. Okay. So you can quickly verify that this and this are exact same things because I have simply added and subtracted the quantity ipa square over 2 quantity square. Okay. So then my integral becomes f of p equals e to the ipx prime square root of 2 pi square root of pi a square minus infinity to infinity dy e to the minus y minus ipa over 2 quantity square over a square times e to the minus p square a square over 4. And notice that as far as the integration over y is concerned, this quantity is just a constant, so I can pull it out. So I can write this as e to the ipx prime square root of 2 pi pi a square e to the minus p square a square over 4 times integral dy e to the minus 1 over a square times y minus ipa over 2. ipa square over 2, sorry, quantity square. And now I do a second change of variables and I'm going to call z equals y minus ipa square over 2. Okay. And then notice that the limits again don't change. dz is the same as dy, and when z is minus infinity, sorry, when y is minus infinity, z is also minus infinity, and when y is plus infinity, z is also plus infinity. But notice that this is not strictly straightforward because z now has a small negative I component. So this is not a simple change of variables, but notice that when when y is plus minus infinity, the real part is very large, so the real part is going to dominate, and whatever the small negative imaginary part is, I can always ignore. So I can write this guy as e to the I px prime e to the minus p square a square over 4 divided by square root of 2 pi square root of pi a square times minus infinity plus infinity dz e to the minus z square over a square. And this is simply a very simple Gaussian integration. And this, hopefully, you already know to be square root of pi over a. So if you don't know this, it might be a good idea to look it up, how this is derived. It's actually pretty easy. So the trick here to do this Gaussian integration is to square this whole integral and then switch to polar coordinates. And then the answer pops out in a second. Anyway, so when all is said and done, f of p is given by the whole bunch of constants. There is a 1 over square root of 2 pi, 1 over square root of pi a square, then there's a square root of pi over a, excuse me, times e to the minus p square a square over 4 minus ip x prime. So notice that I can again do a change of variables, or I can again complete the square to write this as a complete square of some e to the minus p prime square form. But whatever it is, notice that this is also a Gaussian. This is a Gaussian function of p. And this is a very important result. It tells you that the Fourier transform of a Gaussian function of x is a Gaussian function of the corresponding conjugate variable p. So the ft of a Gaussian is also a Gaussian. Okay, so that is what the problem proves to you. And I'll leave it for you to check all the overall factors and things like that if I've made any mistakes. Okay. So let's move on to the next problem. The next problem is work out the commutator of p and v of x. p, v of x. Okay, so this is the question. Now you know, hopefully by now, that to work out the commutator, you have to act it on some kind of a test function, and notice that the result of the commutator is irrespective of what representation I choose to work with. I can choose to work with the x representation or p representation. Whatever it is, the value of the commutator should not change. Since we are more used to the x representation than the p representation, let me work with the x representation. In the x representation, we know that the operator p is minus I ddx, right? Minus I h bar ddx, and x bar is, I can simply substitute by x. Okay. Now, what do I mean by that? I mean that if I have p acting on some state psi, right? Then if I want to project out the corresponding x, which is the x representation, this is basically minus IH bar times the function d psi dx. This is what I mean when I say that in the x representation, the operator p is minus IH bar ddx. Okay, all right. So let's work out the commutator by acting it on a test function. So I will substitute. Okay, so p v of x. I will act it on some kind of a test function. This is equal to p v of x acting on f of x minus v of x p acting on f of x, and this is minus IH bar ddx. V of x acting on f of x is simply the corresponding function v of x times f of x, minus v of x acting on minus IH bar df dx is simply the function v of x times minus IH bar df dx. So to evaluate the first term, I have to use the chain rules. I have to differentiate both of these guys because there is two functions of x. So this is equal to minus IH bar. I'll keep v constant, differentiate f. And then I will keep f constant and differentiate v. The next term is IH bar v of x df dx. And you notice that this term cancels with this term, and leaving me with minus IH bar times dv dx times f of x. Okay. Now I can remove the f of x on both sides, and I can write this commutator p of x, v of x as minus IH bar dv dx. Okay. And if I work it out in 3 dimensions, I will get minus IH bar del v. So this is the answer to this question. This is the result of the commutator. Again, notice that even if I work with the p representation, you would get exactly the same thing. Toward the end of this tutorial, you will understand how to write the X operator in p representation. So you should go back with that information and work out this commutator again in the p representation. Okay. All right. So what is the next question? The next question is, we wrote down the Schrodinger equation as the final postulate of quantum mechanics. So the Schrodinger equation is IH bar ddt of psi equals the operator H acting on psi. The operator H is obviously p square over 2m plus v of x acting on psi. This is the time-dependent Schrodinger equation. We want to write this down in the x in the p representation. So let us look at the x representation first. So when I want to work it out in the x representation, I simply have to take the inner product of this guy with x. So the left-hand side is x d psi dt, and the right-hand side is x p square over 2m psi plus x v of x psi. So the left-hand side is easy to understand. The left-hand side is simply the function d psi dt. So IH bar d dt, the wave function psi x comma t. And in the x representation, as we already know, p is minus IH bar d dx. So this is equal to minus h bar square over 2m, which I can pull out. And this is x d square psi over dx square, plus in the x representation, v of x simply multiplies it with the corresponding function of x. So this is simply v of x, x psi. So the x representation, the time-dependent Schrodinger equation can be written as d dt of psi of x comma t equals minus h bar square over 2m. This is the function d square psi over dx square plus v of x, and this is the function psi of x. Okay. So this is the Schrodinger equation in the x representation. So let us work it out in the p representation. To work it out in the p representation, I have to take the inner product of the Schrodinger equation, which is this equation, with p. So let me do that. So IH bar p d psi dt equals p square over 2m psi plus p v of x psi. Okay. Now two of these terms are straightforward. So this guy is simply the wave function d psi of p comma t dt, which is the Fourier transform of d psi x comma t. And in the p representation, the operator p is simply multiplying by the corresponding number p, because the p representation pp is just pp. And if I take the complex conjugate of this guy, this is p, and since p is a Hermitian operator, this is simply pp, right? So which means that p square over 2m psi, with this p acting on the left here, would simply give me the corresponding number p square over 2m p psi. And this is simply p square over 2m times the wave function in the p representation psi of pt. So the first term and the second term is rather straightforward. So I can write the Schrodinger equation as d psi pt dt equals p square over 2, where this p is not the operator p, but just the number p, psi of p comma t plus this part I have to work out. Okay. Now, essentially, this question is the same as the second question where I'm asking what is the x operator in the p representation, because I have to work out v of x in the p representation. So I'll try to work this out by simply inserting a complete set of states. So I will work out problem number 2 using a slightly more laborious method, but this I will work out by inserting a complete set of states. So you know both methods. Excuse me. Now I know what v of x is in the x representation. I know, for example, if I had this, right, I know how to approach this. Why? Because v of x would act on x to give me the corresponding v of x and x psi. So this is simply v of x psi of x. This is what I used when I wrote down the Schrodinger equation in the x representation. But I don't need this. I want it in the p representation. So how do I work it out? Well, let me use my knowledge of what I know about the x representation and let me introduce two complete set of states. So I will introduce one complete set of states here and one complete set of states here. And I can write this as integral dx prime p. I'll introduce one complete set of states here. So v of x prime, sorry, not x prime, v of x operator. I'll introduce another set of states here, x prime, psi. Okay. So this is using the completeness relation x equal to 1. So this is my first identity and this is my second identity with the corresponding integrations. Okay. All right. But I already know that xp is the wave function 1 over square root of 2 pi h bar e to the minus ipx, right? So this is the eigenfunction of the momentum operator. So if you are unsure of this, go back and check the notes from that particular lecture. So I can write this guy as integral dx prime 1 over square root of 2 pi h bar e to the xp is e to the minus ipx, so px should be e to the plus ipx. Okay. Now v of x acts on x prime. So v of x acts on x prime to give me the corresponding function. So v of x prime, x prime, and then I have x prime psi. Okay, because when v of x acts on x prime, the corresponding function v of x prime can be pulled out, and the overlap of x prime is nothing but a delta function in x. So there is two integrations over x and x prime, but I can use this delta function to make this into integration over just one variable. So I can write this guy as 2 pi h bar integral dx e to the ipx. So this delta function forces x prime to be the same as x. So I can write this as v of x, and overlap of x and psi is basically the wave function psi of x. Okay. But I want, remember, I still want everything in terms of the momentum space wave function psi of p comma t, not psi of x comma t. So let me use the Fourier transform technique. So I will introduce, instead of v of x and psi of x, I will introduce the corresponding Fourier transforms or inverse Fourier transforms, whatever you call this. V of x I will write as square root of 2 pi h bar. Okay, strictly speaking, this has to be e to the ipx over h bar. Right? So that is the momentum space wave function. Sorry, that is the eigenfunction of the momentum operator. Okay. So this is integral dp dp prime e to the I minus ip prime x v of x, and the relation between psi of x and psi of p is also one of Fourier transform, again over h bar 2 pi h bar integral dp e to the I excuse me, this is psi of x e to the I p x over h bar psi of p. Okay. Okay. So I'll substitute these Fourier transforms. I'll substitute these in this equation. So my matrix element, what was my matrix element? P V of x psi now becomes, there is 3 factors of 2 pi h bar. So I will write 2 pi h bar to the 3/2. There is an integration over x, an integration over p, and an integration over p prime. There is a e to the I px, is an e to the minus I p prime x, and there is a e to the, actually I should use some other symbol here because p is already used there. So I will use p double prime, p double prime, p double prime. Okay, dp prime and dp double prime. So there is an, excuse me, there is a e to the I. There is a px from the original integration over here. So px over h prime, h bar minus p prime x over h bar plus p double prime x over h bar. Then there is a v of p prime and a psi of p double prime. Okay. Now I will do the integration over x. If I do the integration over x, what do I get? So I will use the fact that 1 over square root of 2 pi h bar integral dx e to the I over h bar x times p minus p prime. Sorry, this should also be minus because they have this exact same Fourier transforms. So this is a minus and this is a minus. Minus p double prime is nothing but a delta function. This is delta of p minus p prime minus p double prime. Because remember that 1 over square root of 2 pi h bar integral I px dx is delta p. Okay. So using this fact, I can write the matrix element as p v of x psi equals 1 factor of square root of 2 pi h bar goes away. So I'll have 1 over 2 pi h bar integral. The integration over dx is done. So I have an integration over dp prime, dp double prime, delta p minus p prime minus p double prime, v of p prime, psi of p double prime. Now I can use this delta function and to do one more integration over p. And for example, I can do the integration over p double prime. And if I do the integration over p double prime, the delta function forces p double prime. The delta function basically forces p minus p prime minus p double prime equal to 0, which means it forces p double prime to be equal to p minus p prime. So this matrix element can be written, oops, as 1 over 2 pi h bar integral dp prime v of p prime or rather I will do the integration over p prime and leave p double prime because that is the more commonly employed way of doing it. So this forces p prime to be equal to p minus p double prime. Okay, so if I do the integration over p prime, p double prime remains. So this is p prime is p minus p double prime psi of p double prime. Okay, now notice that p double prime is just a dummy variable. So I mean, as well call it some other variable p prime. So this is just 1 over 2 pi h bar. So I don't have to carry through the cumbersome notation. dp prime v of p minus p prime psi of p prime. Okay, so that is what this matrix element is. Now I have successfully written down everything in terms of the momentum space wave function psi of p. So when all is said and done, the Schrodinger equation in the p representation is now given by I h bar d dt psi of p comma t equals p square over 2m psi of p comma t plus 1 over 2 pi h bar integral dp prime v of t minus t prime, the Fourier transform of the potential, times psi of t prime comma t. This is the Schrodinger equation in the momentum representation. So as you can see, it is clearly a little more involved than the x representation that one is used to. The x representation, we have differential operators throughout. In the p representation, we also have integrals and Fourier transforms floating around. Nevertheless, this is the answer to the problem. Okay, so done with this problem. Moving on, the next problem is consider the parity operator. But I will switch the order of doing stuff again. And then I will go back to the second problem because this is a good point to introduce what the X operator in P representation is. So the question is, what is the X operator in the P representation? Okay. Again, I can do it by introducing a complete set of states as we did in the previous problem, but this time let me do it slightly differently and in some sense algebraically slightly tedious, but more straightforward methodology. So what do I mean by the X operator in P representation? First of all, what do I mean by the P operator in the X representation? I mean the P operator in X representation This simply means that if I take P acting on some state psi, and if I project out the X, this is simply minus IH bar d psi dx, right? So we say that I can, instead of talking about the P operator, I can associate with the P operator the differential operator minus IH bar ddx. That is what we mean when we say P operator is minus IH bar ddx in the X representation. So when I want the X operator in the P representation, what I'm basically asking is, suppose if X operator is acting on some state psi, and if I project out the P, what is this equal to? Okay. All right. So let me try to answer this question. To answer this question, let me make use of the fundamental commutation relation between X and P. And as I told you, the commutation relationship is representation independent. So regardless of which representation that I'm talking about, the commutation relations are always true. Okay. So for any state psi in any representation, I know that the commutation of X and P is IH bar, right? So regardless of the X representation or P representation. So let me take the P representation. So P X comma P acting on some state psi is IH bar. I acted on P on the left and psi on the right, right? Okay. And I know what this is. This is just the momentum space wave function. So this is psi of P. I'll forget the comma T for now. I'll just assume that it is a function of P. What is the left-hand side? The left-hand side is P XP psi minus P PX psi. And this is equal to IH bar psi of P. But in the P representation, the P operator, so looking at the second term, acts on the bra P to just give you the corresponding eigenvalue P, right? So I can further write this guy as PXP psi equals the number, minus the number P times PX psi equals IH bar psi of P. But notice that this is precisely what I want, because I am looking for the X operator in the P representation. So I will rearrange this equation and say that Px psi equals Pxp psi minus IH bar psi of P. Okay. So I hope this part was algebraically not too difficult for you to follow. So in order to understand what the left-hand side is, I have to evaluate this particular matrix element. Okay, so it looks like a more difficult matrix element to evaluate, but it turns out that we can evaluate this by inserting a complete set of states in a very straightforward fashion. So let me go ahead and do that. So let's write this down separately. P x p psi. Inserting a complete set of states, and notice using the fact that xp is 2 pi h bar e to the I px over h bar. I'll introduce a complete set of states to work this out. This is equal to integral dx p x p psi. Okay, so where I've introduced a complete set of states here, that is just one. Right? Now I know what this overlap is. Px is simply the Hermitian, it's complex conjugate of this guy. So this is straightforward. So this is equal to 1 over 2 pi h bar under square root integral dx. This is e to the plus I px over h bar. Now this x operator can act on the bra x on the left because x is a Hermitian operator. It doesn't matter if I act it on the left or the right. It's the same x operator. And it's going to give you the corresponding eigenvalue x. Okay, so this is going to be x times the matrix element x p psi. Now notice that this is basically what I mean when I talk about the momentum operator in the x representation, right? This is the momentum operator in the x representation. So this function is basically x minus ih bar d psi dx, which is basically the function d psi of x dx. So this is well known to you. So this whole matrix element can be written as square root of 2 pi h bar integral dx e to the I px over h bar times x, times minus ih bar d psi dx. Okay. So let me clean this up by pulling out the minus ih bar over square root of 2 pi h bar integral dx x e to the I px over h bar times d psi, d psi dx. Okay. In fact, let me write this like this. Okay. So now I can do an integration by parts. This is my dv and this is my u. So this is equal to minus ih bar over square root of 2 pi h bar uv x e to the I px over h bar times psi of x between minus infinity and infinity. Unless otherwise stated, I'm always interested in the region L2 minus infinity infinity because that is the region in which quantum mechanics is generally defined. Minus integral v du. V du is basically psi of x d dx of x e to the I px over h bar dx. Okay. Now, you might be worried about the first boundary term because it keeps growing like x and the e to the IPX over h bar is oscillating wildly. But notice that if you have a wildly oscillating function, it averages out to 0. And also, since psi of x is assumed to be a normalizable function, the psi of x also goes to 0. So anything multiplied by 0 is simply 0. So the boundary term simply vanishes. So there is two negative signs. So I can write this as IH bar over square root of 2 pi h bar integral minus infinity to infinity psi of x ddx of this guy. I have to apply the chain rule. So this is e to the IPX over h bar times dx, which is just 1. So the first term is e to the IPX over h bar plus the second term is x. If I differentiate this with respect to x, I get IP over h bar e to the ipx over h bar dx. Okay. So let me look at everything, see if I've gotten things correct. Okay. All right. So I will write these two terms separately. So the first term is IH bar times the quantity square root of 2 pi h bar integral minus infinity to infinity dx e to the ipx over h bar psi of x dx. That is the first term. Plus, or rather minus, because there is a factor of I here and a factor of I here. So that becomes a minus h bar over square root of 2 pi h bar times another factor of 1 over h bar integral minus infinity to infinity px psi of x e to the I px over h bar dx. Okay. Now notice that I can write this as so. If I consider d dp of e to the ipx over h bar, this is simply equal to ix over h bar times e to the ipx over h bar, right? So I can write x e to the ipx over h bar as the quantity h bar over I ddp of e to the ipx over h bar. Okay, so I have an x over here and an e to the ipx over h bar over there. So I can write this times that as h bar over I ddp of e to the ipx over h bar. And since ddp has nothing to do with dx integration here, I can pull out the ddp outside. So I can write this as ih bar 2 pi h bar. That is the first term. I will leave it intact for now. I hope you recognize what the first term is. And the second term I can write as the h bar here cancels with the h bar here. So I have a minus square root of 2 pi h bar. I can pull out the p and I can pull out the h bar over I. And I can write this entire thing as ddp of minus infinity to infinity psi of x e to the ipx over h bar dx. Okay. So notice that integral psi of x e to the ipx is simply the Fourier transform of psi of x, which is psi of p. And same here. So when all is said and done, the matrix element, which is p xp psi, can be written as IH bar. So notice that the psi of p also involves the 2 pi h bar. Right. IH bar times psi of p minus p times h bar over I ddp of psi of p, which I can write as IH bar psi of p. If I write minus 1 as I square, I get IH bar p ddp of psi of p. Okay, hope I got that one. So let us go back and plug this in our formula, which is this guy in equation 1. So px psi is IH bar psi of p plus IH bar p ddp of psi of p. That is the first term, which is which is this minus IH bar psi of p. Okay, and you notice that this and this cancel, leaving me with IH bar P ddp of psi of p, excuse me. And if I remove the p on both sides, I get p x psi is IH bar ddp of psi of p, which means instead of just like I can write xp psi as minus IH bar ddx, I can simply write the x operator in the p representation as the operator IH bar ddp. Okay, in oops in the p representation. Okay, so that is how you work it out, and I realize that this is a slightly lengthy calculation, but please go through it carefully if you have not done it by yourself, and make sure you understand all these steps involved. Okay, so now that we have done the second problem, let's go back and do the last problem. The last problem, my color changed. The last problem is to consider the parity operator. Phi acting on x is just spatial inversion. And you are asked to understand if the x operator and p operator are even or odd under the parity operation. Well, to do that, we first have to understand what is the combined action of x and p on the either the x state or the p state. Okay. So let us work it out. So the combined operation of x and pi on the x state. What would this be? Well, pi acting on the x state is going to give me minus x. So this is x acting on minus x. And x operator acting on the ket minus x is simply going to give you the corresponding eigenvalue. The eigenvalue in this case is minus x, minus x. Okay. Now let's do it the other way around. Pi x acting on x. Well, x acting on x is again going to give me the corresponding eigenvalue. So this is x times pi acting on x. But pi acting on x is going to give me the spatial inverse of this operator. So this is x times the spatial inverse of this ket. So this is x times minus x. So you notice that x pi plus pi x acting on x is simply 0. Okay. If I add these two quantities, it is simply 0, which means x and pi anti-commute. And by definition of x and pi anti-commute, this means that x is an odd operator. Okay. So now we have to do the exact same thing for the p operator. So let us ask, what would pi acting on p be? Okay. The easiest way to understand this is to simply look at, do the Fourier transform and look at this as pi acting on x. So I can write this as 1 over 2 pi h bar integral dx e to the minus ipx pi acting on x. So this is simply 1 over 2 pi h bar dx e to the minus ipx minus x. Okay, so that is one way of looking at it. Sorry, I made a small sign error here. So this has to be a plus ipx, right? Not minus ipx. The way I would define the Fourier transform. So this is a plus ipx. Okay. So rather I just take this off completely. Okay. That might be clear. Okay, so this quantity is a plus IPX, not a minus IPX as I initially wrote down. Okay, now, so let's pause and go back to this step. Let's try to understand what this quantity is before proceeding. Okay, now notice that in this equation, I can simply do a change of variables. Notice that x goes from x goes from minus infinity to plus infinity. And if I do a change of variables where x goes to minus x prime or minus x, this changes to e to the minus IPX. This changes to minus dx, and the limits change from plus infinity to minus infinity. So I can use the fact that dx changes to minus dx along with the change in limits to write this whole thing as square root of 1 over 2 pi h bar integral minus infinity to infinity dx e to the minus IPX x. Okay, and if p, notice that if p is 1 over 2 pi h bar e to the dx e to the IPX x, then if I have e to the minus IPX, then obviously this whole state should be minus p, right? So pi acting on the operator on the state p is simply going to give me the state minus p by my definition. Now it's easy to understand if the p operator is even or odd. So let's act pi p acting on p. Now p acting on p is simply going to give me the corresponding eigenvalue. So this is the eigenvalue p with pi acting on p, and this is simply p minus p. Now let's do it the other way around. P pi p. This is p. Pi is going to do an inversion of the momentum value, and p is simply going to give me the corresponding eigenvalue, which in this case is minus p. So again, you see that pi p plus p pi acting on p is 0, which means pi and p also anti-commute, which means the operator p is an odd operator, just like the x operator. Okay, so it's actually not very hard to understand why this should also be an odd operator. If you extend it to 3 dimensions, we are talking about vector kind of operators. These are both vector operators. Both x and p are both vector operators. And when it comes to vectors, we do a spatial inversion. The vector becomes negative of itself. So both x and p have to be corresponding to, in the quantum mechanical language, x and p have to be thus odd operators. Okay, so that is basically the answer to the problem.